we need to have some source that creates that potential difference. And that's in this case, that's going to be that battery. And basically what we have with a battery is we've got a device that has two terminals. We're going to have a negative and a positive terminal. We're going to have, on that negative terminal, we're going to have excess electrons, negative charge. On that positive terminal, we're going to have, for our purposes, we're going to call it an absence of electrons, or a removal of negative charge, and so therefore you're left with a positive in terms of the two. But inside the battery, that's a chemical reaction, right? So we're going to have materials, depending on the makeup of the battery, that causes this chemical reaction to occur, so that I get a negative charge on one terminal and a positive charge on the other terminal. And then that sets up that difference of potential between those two terminals, so that I can now control electron flow outside of the battery. I can control a circuit, right? That's what this is. This is walking you through is this chemical reaction between the electrolyte and the terminals, and how you get this negative versus this positive on the terminals. And so the difference in the two. Now, what will happen as you leave this battery sitting for a while, this chemical reaction, it will only occur for so long. And, eventually that battery, because the chemical reaction is no longer taking place, that battery will go back to a stable state. It'll go back to a state where the two terminals are balanced, if you will, and then the battery is no longer any good. It's not going to be beneficial for you to have a battery that there's no difference of potential from the negative to the positive terminal. And so we call that shelf life. How long can that battery be usable, as it is sitting there waiting to be used, as that chemical reaction continues to take place. There was a time many years ago, you used to buy batteries and you just hope for the best. You didn't know how long batteries had been sitting in a pack. You didn't have a date that indicated when they were packaged. Some battery manufacturers now even have a little basically a voltmeter where you touch the two terminals, and it'll give you an indication if the battery is still good. So there used to be a time when you just bought batteries and hoped for the best. And I can't tell you how many times I remember getting Christmas gifts, and everything needs battery at Christmas, right? And so you're getting a Christmas gift and opening up a pack of bad batteries, and being so disappointed because you didn't have batteries to run whatever the model car or whatever it may have been, right? And so as a kid, that was traumatic. But that's a real thing, shelf life. And it's only going to last, that chemical reaction is only going to last for so long. It's only going to be usable for so long before eventually the battery is going to have to be replaced. Now, obviously, what we're talking about there is what we're going to call here is a primary cell, where that chemical reaction is taking place, and it happens over time, and eventually one of the terminals will erode away. They're no longer going to have that chemical reaction that will take place. And if you leave it in a device long enough, you open it back up and you see, it looks like the battery's leaking all over the place and created a huge mess. Those are those primary cell batteries. A secondary cell, that's where we have a slightly different situation, where now we can cause that process to happen over time. We can recharge these batteries, and that's what really we deal with a whole lot of today. And what we see, really the advancements in the batteries that are supporting some of the devices. I mean, you can only imagine how, if you had to replace a cell phone battery on a regular basis, how expensive that would get. It's even your car battery. I mean, it's only good for so long, but it's you can imagine. Now you go and I put a car battery in one of my cars a couple of weeks ago, and they're $150, $200, and so you need that longer life, and so that's what you get out of this secondary cell where you can recharge the battery, and it's going to last a little bit longer. Last a lot longer in some cases. There's your 6-volt.
Oh.
So you can see batteries come in all shapes and sizes, and we're all familiar with a variety of batteries. And all I know around my house is typically the one I need is the one I don't have, right? So I usually can find about any battery except the one I'm looking for. If I need a AAA, I usually got double A's and C's and D's and 9 volts, but I can't find the AAA. If I'm looking for
we used to have a headlamp that used 2 6-volt batteries. That's how I know about that.
A headlamp that used 2 6-volt batteries?
Sure.
Wow.
Wait, a mine?
Yeah.
Oh, Sway.
You carry it as a pack, and then you go out and you use it.
Wow.
Yeah.
Yeah, that's been a while. I don't know many people that want to carry 2 6-volt batteries around now. Yeah.
Nah, they carry 6-volt batteries. Nobody want to be carrying that stuff around. It's too much work.
It's too much work. Yeah.
Sure.
So when we think about batteries, and we've all had devices where I think about the the large flashlight where you just keep loading up the handle with batteries, and it seems like it just never ends. When you're putting those batteries in place, we've all seen what happens when we get batteries that are going in the wrong way. If we've got negative to positive, it's flipped around. We all know how that doesn't work. But the interesting thing here is we're going to look at batteries in terms of connecting them in series or connecting them in parallel or connecting them in series parallel. And so I guess one of the first things we need to talk about is what is series. And I saw in the chat last Monday. So on Monday, I think I saw in the chat that indicated that evidently there's quite a few technicians in this class. And so you guys, probably feel pretty comfortable with circuitry and with electronics. And so that's great. These terms will, you're already familiar with series and parallel circuits. For anyone who might not be familiar with it, when we're talking about series, we're talking about one path for current to flow, right? And if you look at this schematic down at the bottom left, what I have with, this side of the battery being negative, this side of the battery being positive, and we said we're going to talk about electrons, those electrons are negatively charged. That means they're repelled from the negative side of the battery. They're attracted toward the positive side of the battery. And so I've got electrons that are moving counterclockwise through this load, right? They're going through the circuit. And there's only one path for these electrons to flow. There's no options. There's no turns. There's no intersections. It is, one path. They leave, they go through the load, they come back around, and they go to the positive side of the power supply. That's the only path. And so we call that, when there's only one path, we call that series. It's in series. And we connect these batteries, if we're connecting them in series, if I was going to look at, this representation of the schematic, here's the negative side of the battery, right? And so I've got this electrons that would be leaving the negative side. They would go through, let me go back. I accidentally.
Sir, the best way to explain this to us,
yeah,
this is what we work with every day when we work in telephony. Okay.
All right. Telephony. Yeah.
It's a series circuit. We go from the CO to our RG straight circuit. That's the way to explain that to us, and that's that.
Yeah, so it's one
Right.
path, right? It's one path.
Yes, sir.
That-
We are one straight from the CO to our RG, and that's the way it is with the fiber, with
Mhm.
everything we work with. How we're working here in AT&T.
That sounds great. That sounds great. Now, what happens with these batteries? You know, when we're going from one path, you know, negative to positive, and when we're connecting these batteries, you notice I'm connecting these batteries negative to positive, negative to positive, negative to positive. You know, so if I had that flashlight, I'm loading it up, I'm putting them, you know, negative to positive, negative to positive. And what happens, each one of these batteries is 1.5 volts, right? But since I'm connecting them in series, each one of these will add together because they're all pushing current in the same direction. They're all pushing electrons in the same direction. So instead of having a potential difference of 1.5 volts, we add all of those together, and now I get a 6-volt potential difference, negative to positive, right? Everybody see that? That's basically, you know, 1.3 for every one of these batteries. So I get a 6-volt potential difference, negative to positive. Now, the other thing I do get is when we talk about this series circuit, I get current that is consistent. This current is 1/8 of an amp. It's going to be 1/8 of an amp through the entire circuit. We're going to talk about over and over and over how current is common in a series circuit. It's the same throughout. I get this 1/8 of an amp, right? I add my voltage together, I get the same current throughout.
Hey, I got a question about the voltage. Like when you add more, so like, are you always going to end up with the 6 volts, or is that, say you got two batteries?
You end up with however much you add together.
Absolutely.
So if you have 6 batteries, you're going to end up with 9 volts. If you only had 2 batteries, you're going to end up with 3 volts because they're all 1.5 volts for each battery.
Okay, perfect.
Yep,
Thanks.
perfect. Yep, perfect. You're right. You're exactly right. You're just for every battery, you're adding another 1.5 volts when they're connected in series this way.
And where's the 1/8 amp coming from?
So the 1/8 amp, each one of these batteries is rated at 1/8 of an amp. And so they're all 1/8 of an amp. And the thing to see here is that it's 1/8 of an amp throughout the entire circuit, right? And so we
So
add
that never changes. The 1/8 amp never changes for the small batteries per se.
that's right for a series circuit
When you're connected in series.
That's right. For a series circuit, that's not going to change. Now, if we look at parallel, and I'm not jumping over to the next slide so that we can change topics. I'm jumping over to the next slide so we can make a comparison here. When we go parallel, now notice that I am measuring really from the negative. I have all the negatives connected together. I have all the positives connected together, right?
So
And
we're going to increase the current, but keep the same voltage.
Yes,
Is what I'm reading.
Yes. That's correct. That's correct. Remember how each one of these was 1.5 volts? Well, now I've connected all of these negatives together and all these positives together. It's the same voltage. It's 1.5 volts still. It's not additive because I'm not connecting them in series. They're 1.5 volts. However, that 1/8 of an amp current is now all pushing right here on the same line, if you will, if that makes any sense. And so what happens, you increase your current. However, voltage is common in parallel, right? If I had a multimeter and I was going to measure across one battery, I would get 1.5 volts. You know, if I just had it standalone, I measure negative, positive, I get 1.5 volts. Well, if I connect all of these batteries in series and I measure from here to here, in essence, I'm doing the same thing as I'm measuring across the same terminals, this one battery. I'm still going to get 1.5 volts. The voltage does not increase in parallel. What will increase is the amount of current, because now this current of each one of these batteries is pushing not through one another, but pushing along this main line. And so I'm going to go from 1/8 of an amp per battery to a 1/2 an amp, right? If each one of these was 1/8 of an amp, so that'd be 1/8, that'd be 2/8, that'd be 3/8, 4/8. I reduce that down. 4/8 is 1/2 of an amp. That's how I get that 1/2 of an amp.
Okay, so basically backwards. The math is backwards.
it's stable on volts, and then the amps goes up, and the other way it's stable on amps, and then did I say that?
Yep. So
It's
what we,
FTN and then 17 megahertz in our terms.
okay, so when we get to frequency and we start talking about megahertz and we're headed there, won't be there tonight, but yeah, if that makes sense for you in this scenario, okay. But we're going to talk a little bit about frequency and hertz, cycles per second, a little bit later in the course. Really right now in terms of series and parallel, in a series circuit, current is common. The best way to remember that, there's only one path for current to flow, right? So let me go back here. Just take a look at this schematic. The current has to be the same throughout this circuit because there's only one path for current to flow. If I had 1/2 amp here, I'm going to have 1/2 amp anywhere. If I've got 1/8 amp, it's going to be anywhere in this circuit because there's only one path for that current to flow. If we go back to my river analogy, if there's only one path for that river to flow, all the water that leaves point A is going to arrive at point B, right? It's going to be the same. The intensity, it's moving the same amount. Now, when we go and we look at parallel, look what happens with parallel. Negative, right? All of these are negatives. Their negatives are connected together. The positive side of the battery is connected on the other side. Electrons that leave this battery are now faced with an option when they get here, right? Electrons that leave this battery are faced with an option. And so you get multiple paths for current to flow. It's not all these electrons are going to go through each one of these paths. So I have batteries that are in parallel. So all of those currents are going to add up to get to this 1/2 amp. I've got 1/8 of an amp that's coming through this line. I've got 1/8 of an amp that's coming through battery 2, 1/8 of an amp, battery 3, 1/8 of an amp. And so they get here, all of those have totaled together to give me my 1 amp of current that's flowing through this load, right? And so the current is individually, if I measure here, it'd be 1/8 of an amp. If I measure here, it's going to be different. If I measure here, it would even be different because here I would have this 1/8, this 1/8. So that would be 2/8 or 1/4 of an amp, right? And so what is constant in a parallel circuit is voltage. I'm measuring across this battery, it's 1.5 volts. All of these are 1.5 volts in parallel. And so my voltage is 1.5 volts. So current is common in series circuit, voltage is common in a parallel circuit. I will say this, when we get to talking about current flow and resistors, it's going to be a little bit easier to see the difference between series and parallel because we're not talking about this multiple source. This kind of can make things a little bit more cloudy. But the big thing, I got one path for current to flow in series. All the current's going to go through that same path. Current's common. In parallel, just the opposite. If they're parallel, I've got all those voltage sources that are going to be the same, and my current is going to be additive in a parallel circuit. Now, to make things even more confusing, I can talk about batteries in a series parallel circuit, right? I could look at these batteries and I could start to say, okay, what will happen in, for example, this circuit where I have these two batteries that are in series. I say they're in series because there's only one path for current to flow here, but they're also in parallel because I've got multiple paths for current to flow. They're in parallel with these other two batteries. I don't want you to sweat this much. Just realize that when we take batteries, we can use batteries to increase the current, or we can use batteries to increase the voltage, depending on whatever application we may have. let's say that we had a circuit that needed 6 volts, right? Well, I have increased the voltage here by 6 volts. Well, how much current do I need? Well, do I need a half amp? Because that's what I've done with this circuitry is I've increased the current to a half amp. Maybe that's what I need. Maybe I don't. The big thing is I can adjust with any given battery, set of batteries. I can adjust to get to pretty close to whatever current and voltage I might need. The big thing here is just look at these batteries, negative to positive, negative to positive. They're both pushing current up through the circuit. They're in parallel or they're in series. And so I'm adding this 1.5 volts to this 1.5 volts, which, oh no, I'm sorry, that's a 3 volt. This 3 volts plus this 3 volts, which is going to give me a total of 6 volts across, from top to bottom. Same thing with all these batteries. They're all 3 volts. And so I'm getting 6 volts from top to bottom. And then my current
24 volt then.
What's that?
This is 24 volts.
6.
So the total volt is 6, right? Because the only ones I'm going to add are the ones that are in series together, right? So I'm adding this 3 volt battery with this 3 volt battery. If I would take my multimeter and I would put my negative here, my black lead here, and my positive lead here, my red lead here, and measure the voltage, I'd measure 6 volts. I'm measuring across these 2 batteries, this 3 volt battery and this 3 volt battery. When I connect all these parallel circuits together, I'm still going to get 6 volts because I'm measuring across the terminals of each of these batteries in essence. I could be measuring here, but there's so little resistance between in this wire that we're actually going to call this, there's a term called an equipotential point, which means that in essence, this point is the same as this point is the same as all of these other, because it's nothing but wire. So I don't have to worry about a lot of voltage drop in between. So in terms of how much voltage I would measure from top to bottom, 6 volts. Now, each one of these branches has 1/8 amp, right? So if it's 1/8 amp, 1/8, so that's 2/8, 3/8, 4/8 total. Right? We imagine that, 1/8 of an amp of electrons are moving this way, 1/8 of an amp are moving this way, combined with the other 1/8, another 1/8, and another 1/8. I add all of those together, I get 4/8, which gives me this 1/2 amp for my total circuit current. So I wind up with a load that has 6 volts across it and 1/2 amp of current through it. And what I want you to see is really in terms of series, notice that the current through this branch is the same, here as it is here, as it is here. Same with this other branch, because each one of these branches between these 2 batteries are series. It's got to go, if it leaves this battery, there's no choice but to go to this side of the battery and then leaving this battery. So it's all those electrons all flow in those branch circuits. Now, once we get up here, now I start combining those currents. So where I have series, currents common, then I add them up in parallel. When I have my series circuit, my current, since it's common, I'm going to add my voltages together. So I get 3 volts and 3 volts for my total of 6 volts. Just understand that we can take these batteries and adjust them any way that we need to. In fact, well, they don't do it here. In fact, sometimes what we talk about is batteries that are series aiding or series opposing, which means that batteries here, these are series aiding batteries. They're pushing electrons in the same direction, right? And so I add them together, I get 3 volts and 3 volts. Or if I flip this battery around, what will happen if this battery is turned the opposite direction?
Will everything stop working because the flow won't proceed correctly?
It'd still be the same though, wouldn't it?
No, I
So,
think
it's an interesting question because all we're doing is we're taking this battery and we're turning it around. Definitely,
flipping the whole circuit.
What will happen here is these two batteries now are series opposing, which means that one would be pushing electrons up. The other, if I flip it, is going to be pushing electrons down. And so those two are canceling each other out, right? And so now I'm in conflict with this notion of all of these being in parallel, because what happens here, where before, due to the potential on this side of the circuit, all those electrons went this way. Now what happens there? Things begin to get very much more complicated. And in reality, what will happen, just as you said, it's just like when we're putting the batteries in that flashlight and we put one the wrong way, instead of everything being series
Doesn't turn
aiding.
on.
Exactly. Now we have series opposing a battery in, and I don't have enough voltage, and the circuit's not going to work the way it should. Really, do we do a lot with series opposing batteries? Not that I know of, but it's something to be aware of. It's something that we've all experienced at one time or another. I mean, I know for some reason around my house, that little cover on the remote control that holds the batteries in, that thing disappears for some reason. And so the batteries, every once in a while, you got a remote control that's being passed around and boom, the batteries fall out. You put the batteries in once the wrong way, and guess what? Things don't work. It's no longer, and depending on how that circuit is designed, if those batteries are in series, that means that I don't have, the right voltage any longer, because I can't add that 1.5 AA battery and the other 1.5 AA battery. Or if they're in parallel, whichever configuration they may be, I don't have the proper power that I need to control that remote control any longer. So all right, so advantages of connecting battery in series. If we're connecting batteries in series, we're going to have the same constant current. I'm going to be able to increase my voltage, right?
Right.
If I've got 1.5 volt, if I add another one in series, now I've got 3 volts. If I add another one in series, I've got 4.5 volts, and so forth and so on. The current is going to be the same because it's series, right? So I'm going to get the same current, but the voltage, I'm going to be able to add more voltage. Now, the opposite side of that, if I connect batteries in parallel, 1.5 volt, 1.5 volt, I could add as many batteries as I want. If they're in parallel, I still got the same voltage. Voltage is common in parallel, but I'm increasing my current. As every time that I add another voltage, every time I add another battery in parallel, I'm going to increase the current for the circuit. And then if I'm going to connect those batteries in a combination of series and parallel, I can do that to adjust to a specific voltage and current that's needed. If I need a certain set of, a certain voltage and a certain current, well, I can design a circuit that would give me the voltage and current that I needed. Now, let me just say, there's a much easier way to do that than just connecting a combination of batteries, right? What we'll do is we'll take the battery that we need or the power supply that we have, and we will then use other components that we're going to talk about later to control how much current we have, how much voltage we have across the load. And so we have other devices that will actually do a lot of that work for us, especially since we think about in terms of cost. Batteries are going to be much more costly than some of these other devices, much more costly than resistors. Batteries, as we talked, because it's that chemical reaction that's taking place inside, batteries, their lifetime, their lifespan, their shelf life is going to be much less than some of these passive components. And so therefore, really designing the circuit and using batteries to make these adjustments are not necessarily the best way to do it. However, with advances in battery technology, it can take place. Now, how do we identify if batteries are connected in series? What's a good way to tell if these batteries are series or parallel?
You mean
Yes,
like with the
voltage,
multimeter or
negative?
looking at?
Yeah, just looking at a circuit. How would I be able to tell?
It's the positives to go to the negative.
Yeah, and so if I've got a series a connection of batteries, then typically I'm just loading those things up series, negative, positive, negative, positive. They're all in that same direction, and so it's one negative to the other positive. It's all pushing those electrons in one direction, one series path. What about parallel? How are they connected?
Straight across,
yeah.
positives in line, negatives in line.
Yeah, so all my negatives are connected together, all my positives are connected together. So I can look at it real quick and I can tell, is this set of batteries, is it kind of daisy chained, negative, positive, negative, positive, negative, positive? Okay, well, that's series. Is it connected, all the positives to one side and all the negatives to the other side? Okay, well, that's parallel. And then anything other than that, anything that has, a combination of that is going to be series parallel. Okay. Let's take a look at this video.
Hi, I'm Katie with your Galco TV Tech Tip. A battery is a device that is able to store electrical energy in the form of chemical energy and convert that energy into electricity to power electrical devices such as flashlights, smartphones, and electric cars. There are three main components of a battery: two terminals made of different chemicals, typically metals, the anode and the cathode, and the electrolyte, which separates these terminals. The electrolyte is a chemical medium that allows the flow of electrical charge between the cathode and anode. When a battery is supplying electric power, its positive terminal is the cathode and its negative terminal is the anode. The terminal marked negative is the source of electrons that, when connected to an external circuit, will flow and deliver energy to an external device. When a battery is connected to an external circuit, electrolytes are able to move as ions within, allowing the chemical reactions to be completed at the separate terminals and so deliver energy to the external circuit. It is the movement of those ions within the battery which allows current to flow out of the battery to perform work. If the battery is disposable, it will produce electricity until it runs out of reactants. These batteries only work in one direction, transforming chemical energy into electrical energy. But in other types of batteries, the reaction can be reversed. Rechargeable batteries are designed so that electrical energy from an outside source can be applied to the chemical system and reverse its operation, restoring the battery's charge. Batteries come in many shapes and sizes, from miniature cells used to power hearing aids and watches to small, thin cells used in smartphones, to large lead-acid batteries used in cars and trucks, or huge battery banks the size of rooms that provide standby or emergency power for places like computer data centers and power plants. If you have questions and you would like to ask us, you can do so at our technical help forum that's located at forum.galco.com.
Okay, just an example there of some batteries and a little bit of the makeup of batteries. The big thing for us, and I don't hear a lot of feedback about necessarily questions on batteries about the TKT. It's really, since we're getting into circuits and we're going to be talking about power and a source of power, is one of the things that we need to be able to understand is when we're talking about, when we keep drawing the schematic, we're talking about typically a battery. Until we get to AC, we're talking about a set of batteries typically. All right. Yeah, all I can say, I'm reading through the chat, and be careful with batteries, right?
That's the disclaimer, huh?
That's the disclaimer. Be careful. Yeah. Now the thing is, when you I saw in here where it said something about wiring two batteries in parallel won't fry your car's computer, but it will start like a boss on a freezing cold morning. If you got them in parallel, let's just kind of follow that logic. If you got two batteries in parallel, what are you increasing, voltage or current?
Cranking amps.
Cranking amps. That's right. That's
Yes,
exactly
sir.
right. It's the same voltage, right? I mean, if you got those two,
Increase this cranking amps
yeah, that's right.
like a boss.
Like a boss, yeah. Oh, I just mentioned I put a new battery in my car. Like I said, it was about $200. I don't want two of them. That one better do the job. I can't afford two of them.
Heard that.
All right, so let's take a look at. I think we will. Here we go. Let me share this. All right, so let's take a look at resistors and resistance. Resistors, they are devices that oppose current flow, right? And so we're going to talk about these devices through this section and look at a few different types of resistors. We're going to look at, remember I told you early on we would actually talk about the color code, even though I've yet to have somebody come back and say, man, at TKT, asked me 5 questions about the color code of resistors. And so we're not going to spend a lot of time on it, but it's something that is there and you need to be aware of. And you need to be able to, when you see it, at least know what it is. And then, so we'll go through and we'll talk about resistors and what they're for and what it actually does, right? And so resistors, resistance, the opposition to current flow, the opposition to the flow of electrons. We've got several devices that we will introduce later that uses this notion of opposition a little bit differently, but to start off here, opposition, this is a constant, steady opposition to current flow. This is the rock that's in the water's path, right? That rock doesn't change. It's the amount of resistance that it is, no matter how much current is flowing through that particular pathway. It's that amount, that set amount. And so we're going to look at some resistors that we can adjust, but even then, once we adjust it, it's set. I mean, it's a given amount. We're going to see devices later on that will shift and will change their opposition based on some factors, but this is a opposition to current flow all the time. Doesn't matter how much current is flowing in the circuit. If it's a little or a lot, it's still the same amount of resistance. We're going to measure that resistance in ohms, OHMS, ohms. And, typically we'll use that Greek letter omega as the symbol for ohms. And so if you see, something that says, 25, and then that letter omega, that's ohms, 25 ohms. We're talking about the value of resistance. In terms of a couple different factors that really determine the resistance, you can make these resistors out of different materials, and the different types of materials will have different values of resistance, based on the material and what we looked at earlier, the atomic structure. The cross-sectional area, the larger the device, the less the resistance. The smaller the device, the greater the resistance. And we're going to look at some different resistors, and we'll talk about exactly what the size of the component means. One way I'd like, you can think about this cross-sectional area and resistance. It's just like if you had a hose, a water hose, and if it's a small cross-sectional area of a hose, you're going to have much more pressure, right, for any given amount of flow. If it is a larger hose, that water is going to flow through that hose with less resistance, and therefore you don't have as much pressure buildup. It's the same process of you putting your finger over the end of a hose, reducing the amount of cross-sectional area of the water to flow, and it increases the pressure. In many ways, it's the same thing. If I take a conductor and I reduce the cross-sectional area of that conductor, you're going to have greater resistance versus a larger conductor. And then the other thing is the length of the conductor itself. The greater the length of the conductor, the more resistance that it's going to have. And so cross-sectional area, it's inversely proportional. Increased cross-sectional area, decreased resistance. Length of a conductor, they're directly proportional. Increased length of conductor, increased resistance. Here's an example of a typical resistor that's been cut away. You can see the color bands on the outside of it. It's made up of this carbon composition on the inside. You've got leads that will go from the rest to the circuitry. The whole purpose of this resistor, it's opposition, right? We said resistance is the opposition to current flow. The whole thing it's going to do is limit current flow. It's going to develop voltage, or we may say drop voltage. And when we start looking at resistors, we'll be able to calculate and measure voltage drops across each resistor, or the amount of voltage that's developed across each resistor. And so really, you're thinking about using these resistors, it's those two things. It's limit current flow and develop voltage. You go back to thinking about our last PowerPoint where we're talking about all of those batteries in different configurations. And we were using those different configurations to give me what I needed from a voltage standpoint and a current standpoint. Well, I can do the same thing with a schematic, a certain design of resistors. I can have more voltage than I need, more current than I need, and then use my resistors to drop voltage down. I can use those resistors to limit the amount of current that would be going through the load.
Is that going to drop it down for the whole circuit, or say, can you place a resistor like right before a load just so it can drop it down for that specific load, and then it'll be higher across a different part of the circuit?
That's a really good question. And yes, I was hoping that we might have a schematic that would kind of show some of that. You're 100% right. I can put my resistor in series with the load right before the load, and then it's going to drop the current down just for what I need going through that resistor. It's going to be the same current that's going to go through. The other thing I can do, because remember, that's a series circuit, current's common in series. The other thing I can do is I can also put a resistor in parallel with a load and develop voltage across that resistor. And then
Across that
remember,
parallel circuit.
yeah, and so remember, in parallel, voltage is common. And so now I can use that resistor to develop whatever voltage I want and put it in parallel with the load. Bam, I have the voltage that I need at that point. And so, yes, I can use those resistors either in series and parallel, that combination, to get exactly what I want going through the load, whether it be current or voltage. Yes. And that's what we're going to do as we continue to move forward. We're going to take a look at some circuits that do exactly those things: voltage divider, current dividers, circuits that will adjust my source to exactly what I need for my given load. In terms of composition of resistors, carbon resistors like the one that we just saw. You also have wire wound resistors, which is really what it sounds like, a conductor that's wound, made up of many turns, if you will. And then I can even have that those turns make it where it's adjustable if I want to select only a portion of the turns or even more. And so we'll see some of that as well. Up here on top left, you see something that looks like the schematic of a potentiometer or a rheostat. It's really just a knob that you're going to be able to turn, and this window, this wiper, is going to adjust over the turns. And so my resistance that I will feel between these 2 points is going to change. It's going to be based on how many of these turns of wire that I'm actually going through. And so I could increase it or decrease it. That looks like a dial to us. It's same thing. If you had a light switch and you had a rheostat like that, where you could turn and change the resistance, and as you change the resistance, it changes the amount of current that flows through the light bulb, and so the light bulb gets brighter or dimmer based on how you're adjusting that resistance. That's what fixed resistors, one specific ohmic value. We're going to see that amount, and it's going to be that amount until it fails. And I'll tell you this too, in terms of resistors typically, they're not the problem. Typically when you're troubleshooting, it's not that a resistor has failed unless things have really, when they do fail, it's easy to see, because what'll happen is they'll heat up. You'll see a lot of black. You'll see some burn marks.
Yeah, it's smoked, right?
Absolutely, you can't miss that carbon smell. But typically that's not the problem. They're pretty steady. These tap resistors, kind of like the one that I was just showing you, in terms of adjustable, wire wound. We're going to see, I think, another example of those. These adjustable resistors that are single resistors. Those are some that I think we'll take a look at. I think we've got a couple pictures coming up. Potentiometers and rheostats, they're basically the same thing. It's just that one has 3 leads, the other only use 2 leads. In fact, we'll probably see a rheostat that is nothing more than a potentiometer with one of those leads clipped off. And so here's what we have. We have this fixed carbon. This is what we're going to see most often. You're going to see the schematic symbol that will, it's there. It is. That's what we're going to use in our circuits. You have this tapped wire wound. Now this is a wire wound resistor, and so it's got these windings around this core, and then you've got this tap in the middle, and you can adjust this tap to set it. But once you set it, it's set. You just kind of you set it where you want it, and then you leave it. You don't go in and adjust it. There's in circuit, if you will. Here we've got an adjustable wire wound, and so this gives me an opportunity to make some adjustments in circuit. And then more than likely, when you're talking about something that's an adjustable resistor, you'll see something that looks like this potentiometer. Notice the 3 leads here. 1, 2, and 3. And so as I adjust this knob one way or the other, this wiper will move, and you can see that between these two, let's say the wiper moves to the right, between these two leads, my resistance would be decreasing, but between these two leads, my resistance would be increasing as this moves to the right. And then, for what we have here, this rheostat, it's the same thing. It still has the 3 leads. It's just that we're only using 2 of those leads. Say we're going to use, this side, and the wiper and one side, so that we can, as we adjust, we're going down or we're coming back up.
So the potentiometer would be like the AC fan mode, or like the windshield wiper speed.
Yeah. It could be if if I have a circuit where, especially if I'm looking at, let's say from this potentiometer, I'm driving a load that I want to either increase or decrease as I move this knob, right? As my resistance changes, then my current through that load is going to change. But then I can also, with that third lead, continue to maintain another portion of the, if I got 2 things that I want to move simultaneously, in other words, I want to make some adjustments that, whereas one would increase, the resistance over the other would decrease, and vice versa, right? And so I can use that potentiometer in that unique situation. More than likely, what you're probably going to do is use a rheostat, where that rheostat, as I make an adjustment, the resistance is going to change. If it's in series with it, and I decrease the resistance, I've got more current going through the load, and I get a brighter light. If I turn it down, I've got, or if I turn it the other direction where I've got more resistance, it's in series with the light, and so I've got less current now going through the light, so I've got a dimmer light. So that's going to be that rheostat, where that a potentiometer is, like I said, it's not used as often, because I can actually control with this one knob. I could control 2 different devices, if you will, in the opposite direction, because I'm going to increase or decrease as I move this wiper from one side or the other.
All right.
All right, now the color codes that we're talking about, all of these carbon resistors are going to have colors on them, and there's many different acronyms to remember the color code. Here's an example. Bad boys rob our young girls, but Violet gives willingly, get some now, right? And so this is there's probably, I've heard probably 40 of these different things over the years, and so this is just a matter of what can you hang on to remember that these colors, and then to be able to place values to these colors, right? So if we look at this chart, here we have that bad boys rob our young girls, but Violet gave willingly, get some now, right? Get some now. Notice that there's no N here for get some now. This N is actually no color band, and so there's nothing on the chart. But when we talk about that acronym, when we go through that saying, if you will, this is what the colors are, black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. And then all we have to do is think about, okay, each one of those bands, I got my number for the first color, I've got a number for the second color, then I've got a multiplier, and then I've got a tolerance band, right? And so I'm going to have at least 3 colors on a resistor. I could possibly have 4, A lot of times I'll have 4, but I could have only 3 because this tolerance band, if there is no tolerance band, then it's going to be down here. It's 20%, right? So let's see if that makes any sense here. First of all, notice we've got 4 color bands. Where do you start? You always start with the band that's closest to the end of the resistor. You can see that this band is closer to this end than this band. You start with the one that's closest to the end of the resistor, and then it is a matter of just identifying the color, right? So Bad Boys, Rob, our Young, which was yellow, right? Now here's the trick. Don't forget the first color is 0.
0.
0,
I was
exactly.
like, that's not 4, that's 5.
That's 5. Exactly. Don't forget that the first is 0. And so
Out here
therefore,
counting by zeros.
got to make things hard, right? So that's why you're going to look, this could be the 5th color, right? And if you go continue on, Violet, Bad Boys, Rob, Our Young, Girls, but Violet, that's 8. So there you go, 7. And then the multiplier band, Bad Boys, Rob, and so that's a 2. That means it's got 2 zeros on it, right? So that is 4700. A tolerance band of silver, which is 10%. 4700. If we offer, we write that in engineering notation, is 4.7 K. So 4.7 kilo ohms with 10% tolerance. To calculate the tolerance, all you have to do is multiply the value by 10%. You're going to subtract 10% and you're going to add 10%, and then you get a window, right? And so for this one, looks like you would have 4.23 K to 5.17 K would be the range. 4.23 to 5.17. You can see as this tolerance band changes, that was 10% tolerance. As it gets, let's go back. As this tolerance band, gets away from these values and into, like, say, these values, you're talking about some precision resistors at that point. For the most part, we're probably going to be operating down here. You're going to see gold, silver, or no tolerance. Really, that
And then
variability.
those plus or minus 20.
Yeah, no would be plus or minus 20. Yeah, and so I mean, you're not going to see a lot of precision resistors for the most part. We're just going to get close enough, and we'll be fine. You may see some precision resistors if you get into some highly specialized equipment, but for the most part, everything you're going to see is going to be down here. So it's not hard.
Is there a reason for precision resistors?
Well, when you get into an application where you really need to make sure that your everything is in a tight tolerance, you could use precision resistors. The only thing is, it's like a lot of things in electronics. There's another way to do that, and everything. Well, a lot of times, how things are. They boil back down to money. And precision resistors are going to be more expensive than some of these higher tolerance resistors. And so we just get into the ballpark, and then when we look at power supply, we'll see how we can use some other components to get us right where we need to be in terms of our voltage without having to use precision resistors. But yeah, I'm sure there are applications that use precision resistors. It's just, for the most part, you're not going to see a lot of it. So you can see it's not. What was that?
I said right on. Yeah,
Okay.
plus or minus 0.05%. Like, come on.
Yeah, exactly. right? And you guys, if you've done any troubleshooting, you know, when you're in a circuit and you're looking at a schematic and it calls for 12 volts. If you take a measurement and it's 11.7, okay, yeah, you're good, right? Yeah, I mean, for the most part, most of the circuits that we're going to be working in, it's not to that level of precision anyway. That's pretty tight there. So it's not really difficult to do this, right? I mean, you spend a little bit of time and you can remember a saying. If it's not this saying but another saying, you can remember those colors, and then you can kind of recreate quickly these first three columns at least, because it's all how many really. All I have to do is count what number down the line it is and make sure I don't forget zero, and that tells me the number, and then how many zeros am I adding, and I've got my value, right? And then for the most part, if we're working down here in terms of our tolerance, it's not too difficult to recreate this chart in your head. Now, the good thing is we don't have to do that, right? I mean, we can always go and measure the resistance of these resistors. We can make sure that we are kind of have an idea of what it should be, and then I can take my meter. If I measure across the resistor, I can get a value. If I have my meter on ohms, it'll give me a value. Now, one thing I have to make sure is that if I'm going to measure the resistance of a resistor, I can't do it in circuit. I can't leave the resistor completely in circuit and measure across that resistor, because other devices or other components or whatever else is in the schematic, whatever else is in the circuit will impact my reading. And so if I'm going to measure a resistor, I have to at least lift one leg of the resistor from the circuit, and then I can measure in parallel with that resistor to get a ohmic value. And we're going to see how that plays out as when we start to do some calculations on these circuits. We'll see what happens when I start to add resistors in series or parallel. Now, one of the things that we need to think about is wattage. Now, wattage, that's the value for power, right? When we're talking about power, we threw up Ohm's law at one point as we were working with some of the math, and we said voltage is equal to current times resistance, and that's Ohm's law. Well, for power is equal to current times voltage. I know it sounds very similar, but you'll get used to the difference and you'll see the difference. One of the big things about power is in terms of these devices, when you have a device that resists current, right, resists current flow, it's going to develop that voltage, right? It's going to reduce current flow. And so something has to happen, as you've got this device in circuit and you're trying to push electrons through this device, and it is trying to limit the amount of current flow, and it's developing voltage across that resistor. Well, that power, that wattage, what happens is we get heat, right? We get, depending on how much current and how much voltage, the more voltage, the more current, the more heat, it's more power, right? And one of the things that we can look at a resistor and tell is its wattage rating or its ability to handle power. If you look at these two resistors in terms of the current that's flowing through these resistors, I can't tell what the colors are for the smaller resistor, but it could actually be more resistance than this larger resistor. We can see the values here And so we could go in and we could calculate what the resistance is. And actually that looks like one that we just calculated, you know, maybe a 4.7K. So we could tell by looking at the colors, which one of these is the larger resistor in terms of opposition to current flow. The size doesn't make a difference in terms of opposition to current flow, but what does is what this size does make a difference in is its ability to handle a certain amount of power. In other words, what I'm trying to get around to saying is that the larger resistor has a higher wattage rating than the smaller resistor. The larger resistor is going to be able to dissipate more heat just because it has an increased surface area. Smaller resistor, it's not going to be able to handle as much heat. You know, if you put the same amount of power through this resistor, it will burn up faster than this resistor. You know, this resistor is going to be able to dissipate heat. This one's not. Eventually, this one's going to fail. This one is going to still be able to continue to dissipate that heat, handle that power until up whatever the rating may be for this particular resistor. That makes sense. Power is heat, right? For resistors, power equals heat. And the larger the surface area, the more heat you can dissipate. The smaller the surface area, the less heat you can handle, less power you can handle. Questions about that? Okay. If you think about, think about, your car and, how you're getting rid of the heat that is generated by the engine in your car, right? And so you've got surface area, a large amount of surface area that's created by the different components in your car, right? And so the larger the surface area, the more heat that's going to be dissipated. If you take a look at a computer and you look at the microprocessor, which generates a lot of heat, you're going to have a heat sink that is connected to that microprocessor and some other means of dealing with that heat. But that heat sink creates more surface area. It generates a larger surface area that will allow that heat to dissipate instead of burning up that device. Same thing is true here. If I got a smaller resistor, smaller in size, physical size, it will not be able to dissipate as much heat as a larger resistor, just based on the surface area. A thermistor is a different type of resistor. Basically, that resistor will change values based on temperature. And so, as the temperature changes, the value of the resistor changes, which is useful. It makes it, you can use it for different applications. One application is that since the resistance is going to change based on the temperature, you can certainly use it to evaluate the temperature of different items, right? Because if you know that it's calibrated at a certain temperature, the resistance is going to be X. If the temperature increases, the resistance of the thermistor is going to change. And as it changes, you can then have a scale that would read out a different temperature. And so we have those devices. You can also use a thermistor in safety, for safety purposes. If you wanted to have a thermistor, it's been a while now, but I remember, gosh, it's been a long time. It's probably been 20 years. I remember I used to live in a house that had one side of the house had a large glass window and a loft up top. And I remember seeing a reflection down into the kitchen below, and this flashing, yellow gold light that was coming from the kitchen. Well, it was a microwave that was on fire. you know how it is. Kid places something in the microwave that doesn't belong. The next thing you know, it catches on fire. The microwave had cut off, right? Whatever was inside was aflame, but the microwave had cut off basically due to a safety feature, a thermistor that they had placed on the backside of the heating chamber. And so whenever you know you get a fire in the chamber, it would cause the thermistor to change resistances because it is heating up, and as it changes resistances, bam, you have another circuit that's triggered and power is disconnected. You know, it's this safety area is tripped. So you know, you can use this thermistor, this notion of changing resistance based on temperature. There's a lot of different applications for it. So AWG, American Wire Gauge, you guys are probably familiar with AWG. You know, basically, when you think about AWG and you think about the cross section of the wire, you know, it seems like it's hard for some folks to grasp because, you know, the numbers get smaller as the wire gets bigger, right? And vice versa. And the number really, you can think of it in terms of resistance, because as the number goes up, the wire gets smaller. Well, the amount of resistance also goes up for that given amount of wire. And so in terms of wire size and resistance, they're inversely proportional, just like the way the wire is gauged. And some examples: twisted down below. Okay. All right, let's see what we got. Now, with all of these, you know, the two areas that we've talked about tonight, batteries and resistors and resistance, you know, you've got these quizzes that are in your course, so you can go in and take those quizzes, see how things go, see what you have questions about, and you know, we can, you know, if you do that between, you know, this class and Monday, then, you know, we can you know, hit any questions that you might have there. So like I said, those quizzes are not for me in terms of grades, they're for you in terms of just a knowledge check. So use those quizzes as a way to you know, reinforce and learn the material. All right, so actually, I'm going to do this. We'll take a look at this resistor and resistance video, and then that should put us right on a break before we get into the next topic. Because I think once we dive into the next topic, might take a little time. Let's see.
Good morning, welcome back to episode 5 of Electronics. In this episode, we are going to talk about a very important electronics component that we are going to be using a lot, and it is the resistor. The resistor is very important, and we are going to learn all about it. Now, in the last video, we talked about resistance, which is measured in ohms, or you might see this symbol around somewhere. And resistance is very important to have in a circuit. And a resistor basically provides a circuit with some amount of resistance. It will actually resist the current, however many ohms that resistor is going to provide. And trust me, if you don't understand all this, we will learn all about it today. And later on in the video, I'm actually going to show you a real resistor and we're going to work with it. Now, why in the world do we really need resistance? Well, let's say we have a battery here and it has two terminals here at the top. Who cares what they are right now? Just know we have two wires here. And these wires, let's lead them up to a little light bulb, and this light bulb is giving off a bunch of light. Now we are going to do something similar to this in a couple of videos, and this actually will not work in our case. The battery, in this case, just imagine, is providing a ton of current to the light bulb, and the light bulb can't handle it. And this might actually burn out the light bulb and cause the light bulb to be not able to work. Instead, we need to resist some of the current. That way we don't overload the light bulb and it'll blow out. So in this case, we would add a little resistor into this wire right here. And that will help resist some of the current. That way the light bulb can actually work. Don't worry, we're going to get all into this in a little bit. So before we get started here, I want to point out a few things that you might see along your journey. You may see something that says 1 ohm, and that means 1 ohm. But you might also see something that says 1 k ohm. This stands for 1 kilo ohm, and that's actually equivalent to 1000 ohms. You may also see something called 1 m ohm, and this stands for 1 mega ohm, and that really means 1 million ohms, and I spelled that completely wrong, 1 million ohms. I just wanted to point this out. These are just 3 different units. You have ohms, which are regular, what you're going to use in equations and all that. Then there's 1 kilo ohm, that really just means 1000 ohms. Then you have mega ohms, that really means million ohms. So you could have, say, 2 mega ohms, that's 2 million ohms. Maybe you have 20 kilo ohms, that's 20,000 ohms. Just something I thought I should point out. There are multiple types of resistors, but the most common one that you'll see, and hopefully the ones that you're going to be getting, look a little bit like this, and I'll show you one later on. But basically, it's a little component and it has 2 wires coming out the ends, and it has a little body here. This is a resistor, except how in the world do we know if this resistor is a 10 ohm resistor or maybe a 1 kilo ohm resistor or a 1000 ohm resistor? How do we know what this resistor is going to provide to us? Well, these resistors actually have little color bands on them. So say this resistor has a brown color band, then say it has 2 black color bands like so, and then say it has a red color band at the end here. These color bands will actually tell us how many ohms of resistance this resistor will provide for our circuit. I know that this color band arrangement means this resistor will resist 10 ohms of resistance. Now, how in the world do I know that? Well, I didn't memorize it. I actually have a very handy chart over here. You can get this chart on my website. I recommend that you print it out or save it somewhere that you can access easily, because this chart is very important. You're going to be using it a lot, and I'm going to teach you how to use it. Basically, we are going to look at the very first color band. In our case, it's a brown color band. So on the chart, you're going to go over to the first column, and we're going to see under brown is the number 1. So we're just going to write down the number 1 here. The second color band is black. So we're going to go under the second column here, go under black, which is 0. So we're going to put 1, 0, like so. Then the third color band is also black. So we're going to look under black, and we're going to go under the multiplier. The third color band is called the multiplier band. In our case, black, which is our third band, is a multiplier of 1. And that basically means take the number that you already have, in our case is 10, and multiply it by 1. This will give you your final resistance value. In our case, 10 times 1 is 10, or 10 ohms, like so. Now, what is this red band for? Well, the red band, or the last band, whatever color it is called your tolerance. If we look under the chart here, red has a plus or minus 2% tolerance. Now, don't worry about the tolerance that much. We really don't care about it. Tolerance is basically how accurate is this resistor. Plus or minus 2% tolerance means this resistor, in our case, might be 10 ohms, but it could be a little bit under 10 ohms, or it could be a little bit over 10 ohms. It's not going to be exact. But if we had a tolerance of, say, a gray color band, so plus or minus 0.05%, that is an extremely accurate resistor. That resistor is going to be as close to the rated value as possible. It's not going to vary that much. For the things that we are going to be using resistors for, it's okay if you have a gold band, plus or minus 5%, that's plenty. Even silver might work for a lot of the things that we're doing. So tolerance is basically how accurate is the resistor. We don't really care about that right now. We just care about the first, second, and multiplier bands. So let's try a different example here. Say we have a resistor that has a red band, and we'll do a black band. So we have a red band, a black band, and we'll have a green band here as well, and we'll have another green band at the end here. So this is our resistor. How many ohms is this resistor going to provide us? Try and figure it out yourself right now. Well, if we take a look, our first band is a red band. So under the first column, red is 2. So we're going to write down the number 2. The second band is black. If we look under the second column, under black, we have 0. So 20. Then our third band is green. And remember, the third band is the multiplier band. So under green, we have to multiply this by 100,000. So 20 times 100,000. And that is going to get us our final resistance value. In this case, 20 times 100,000 is, I believe, 2 million ohms. You could also write this as 2 ohms, 2 mega ohms, like we talked about in the beginning of the video. And of course, this resistor has a tolerance because we have another green band of plus or minus 0.5%. So it's a fairly accurate resistor. That's pretty good, but we don't really care about the tolerance. Who cares about that? So hopefully you know how to find the value or the resistance value, the ohm value of a resistor. Now let's actually take a look at an actual resistor. Okay, so here we have two actual resistors. Here we have a 1 kilo ohm resistor at 5% tolerance because we have a gold band at the end. And the bottom resistor here, we have a 75.1 kilo ohm or a 75,100 ohm resistor at 1% tolerance. Notice how the bottom resistor is different than the example. It actually has 5 bands on it. It's kind of hard to see, but the first band on there is purple, green, black, red, and then brown. This means you just take the purple, green, and black ones and do the digits first. Then the red band would be the multiplier, and of course brown is still the tolerance level. The top resistor here is almost the same as the examples. It only has 4 bands, so you can just follow the examples with that one. Get used to seeing these resistors because we're going to be using them a lot. Thanks for watching, everyone, and I'll see you.
The other thing about those resistors, notice that they are the same size. And so that means that they are also the same power rating. All right, so we are, let's see, at 8:35 your time. So let's take a 10-minute break and come back at 1:45. All right, so see you guys at 8:45. There's always a band that's closer to one end or the other, right? And so you'll have the first band will be the closest band to the end. Let me pull up a resistor and I'll show you what I mean.
But to which end though? Because there's 2 ends, and sometimes they're like really close to each side. You know what I mean?
It could be that they're close, but you should be able to tell the difference. One should be closer to the end than the other, right?
So maybe it's just not very visible on a screen like that with the picture.
Oh yeah.
In practical application, it's going to be easier to see. You'd be like, oh yeah, that's definitely this side.
Absolutely. So
Okay.
let me show you this picture. And it will be, there'll be times. I mean, even here you'll see that it's close. So like these two, this is a little bit closer than this side. You can also notice how this tolerance band, see how there's more distance in between this third band and this tolerance band?
Oh, I guess it would also help because the tolerance, no, never mind. The tolerance band could be any color, right?
Yeah.
It can be, but keep in mind what I was saying. Most of the time you're going to see those tolerances. It's going to be exactly
Yeah, gold, silver.
gold,
Silver, or nothing.
Or nothing, exactly. And
Probably
so
nothing.
that's a dead giveaway. You don't have many resistors that are going to start off with, gold or silver. This top, you can see that this is a little bit closer than here, but that looks like it may be gold. So same thing. You also notice in between that third band and the tolerance band, there's usually a little bit more space there. They seem like they're uniform, and then there's a little bit more space, but it should be closer to one end. And I think it's easier to see on typical resistors when you're holding it in your hand. I don't remember there being a whole lot of is it that end or that end? So I think it'll be obvious to you.
All right, thanks.
Yep, no problem. All right, so let's take a break. It's 8:40, so 8:50. All right, sound good? 10 minutes. Okay, let's take a look at some of these laws of electricity. We're going to go through and we're going to talk about a couple different things, couple things that we've mentioned before: Ohm's law, Kirchhoff, however you want to say that. Typically say Kirchhoff. Kirchhoff's voltage law, current law. Take a look at power and talk about how to calculate some of these things and look at how we can evaluate and eventually even take some measurements to evaluate these components and circuits. So as we look at Ohm's law, we mentioned before Ohm's law, we were talking about current and voltage. Ohm's law is that relationship between current, voltage, and resistance. We said that voltage is that difference of potential. We talked about some batteries and having that potential difference between a negative terminal and a positive terminal. Current being the amps, the amount of flow, electron flow in the conductor. If we would take a measurement at any given point, we'd be able to measure so many electrons, so much charge that's moving past that point. We're going to call that intensity, or I for current. And then finally, resistance. The resistance is the resistance that's in the circuit. It typically at this point we're really focused on those components that we just talked about, those resistors in the circuit. Know that there is some resistance even in the wire. There's you can't help but have some basic small amount of resistance. However, for our purposes, when we are doing these calculations, we pretty much just disregard the resistance of the conductors, and we focus on the resistors themselves. I mean, because the amount of resistance that are in those components is much greater than the conductor. And so, but just be aware, there is some resistance there in the conductor. As we talked about, the longer the conductor, the more resistance that you're going to have. The smaller the cross-sectional area of the resistance of the conductor, the more resistance you would have. Now, you can see this formula, and we talked about last Monday, or on Monday, we talked about this notion of directly proportional and inversely proportional, and how current and voltage are directly proportional. As my current increases, my voltage increases, or vice versa, and how current and resistance are inversely proportional, which makes sense. If resistance is the opposition to current, then if I get more resistance, I have less current. So you can see the formulas here, and this is the same formula. Don't forget that E is voltage, also could be V, right? I mentioned that we do a bang-up job of switching it back and forth on you guys to get you accustomed to seeing either. So, if you see V, voltage is equal to current times resistance, or E, voltage is equal to current times resistance, it's the same thing. This formula is the same formula. This is Ohm's law, and we've just solved it for each one of the variables. The easiest one I think to kind of start with is just remember voltage is equal to current times resistance. And then from there, you can solve that formula for anything that you may need. Now, this little trick is a quick cheat. Like if all you have to do is be able to remember voltage is equal to current times resistance. I put my voltage on top, and if whatever you're solving for, cover it up with a finger, there's your formula, right? If you're solving for current, it's voltage divided by resistance. If you look at our formula as we manipulate the formula over here, current is equal to voltage divided by resistance. So if I'm going to solve for resistance, well, that's voltage divided by current. Resistance, voltage divided by current. Or if I'm going to solve for voltage, I cover up the voltage. I'm left with current times resistance. Voltage is equal to current times resistance, right? So pretty easy to maneuver back and forth there with that Ohm's law, with that formula. Kirchhoff's laws. Now, Kirchhoff, there's a couple different things that Kirchhoff states. One is Kirchhoff's voltage law. And really what Kirchhoff does is he takes a look at a circuit and a closed loop of the circuit. And basically what he says is that the voltage, the sum of the voltage drops is equal to the voltage applied. In other words, if I would take a look at a circuit, if I had, in this example, 3 resistor circuit, voltage across R1 is 2 volts, voltage across R2 is 4 volts, voltage across R3 is 6 volts. The applied voltage is 12 volts. Let me see if we got an example of that. Nope. Didn't want to go there. Man, how did I skip so many? All right, so if I've got this circuit, let me see if I can annotate this. And basically what it's saying is that if I had a circuit that looked something like this will not be pretty. That's okay. We'll get to the idea. And so if I've got that circuit and we said R1 is 2 volts, R2 is 4 volts, and R3 is 6 volts. My applied voltage was 12 volts. And so what Kirchhoff says in his voltage law is if I take a closed loop, you can see this is a closed loop, right? So everything is going to be accounted for. And if I would just go around the loop and my voltage applied is going to equal the sum of the voltage drops, right? So 12 volts is applied. I go through my voltage drops, 2, 4, that's 6, plus 6 is 12. That's what Kirchhoff says in terms of his voltage law. Now, sometimes it may be stated slightly different. Sometimes you'll hear it stated as the algebraic sum of the voltages equals 0. All that means is that if I would go around this circuit and I assign algebraic values to where the voltages are applied, let's say that's positive, and the voltages that are dropped are negative. If I said 12 volts minus 2 volts minus 4 volts minus 6 volts equals 0, that's saying the same thing. Whether you say that the voltage applied is equal to the sum of the voltage drops, or whether you say the algebraic sum of all the voltages equals 0, you're basically saying the same thing. If I have a circuit and I apply 12 volts, and when I look at my circuit, if I've only got 10 volts accounted for, something's wrong. I've miscalculated something. I've done something wrong, right? So the algebraic sum of all the voltage drops should be 0. Applied should equal what's dropped. that make sense?
Yeah. So do they ask, right here where it shows right after 2, do they ask how much voltage is between 2 and 4? So which would be like the 10 volts that you just said?
Yeah. So if you were going to, like, let's say, I think what I hear you saying is let's say it was something like this. And let's say that's just point A and maybe point B. And so they could ask you something like, what's the voltage between point A and point B? Then yeah, it would be a total of 10 volts that are dropped between point A and point B.
Okay.
Yeah. Now, keep in mind, you see how that's different. And I know just because you asked the question the way you did, that's different than what Kirchhoff is saying, because he's talking about the algebraic sum of this entire closed loop, right? And when we get into, a little bit different circuit where we're no longer talking about a closed loop, things get a little more complicated. So that's a little bit different than what Kirchhoff is saying, but you're exactly right in terms of your statement about you could take a measurement and ask how much voltage is dropped here, at between R1 and R2. Yes.
Okay, thank you.
Mm-hmm. So that's his voltage law. Now, let me change that. Now, Kirchhoff also had his current law, and notice that, I'll go back one more time. Notice that in his voltage law, right, when I drew that circuit up, that was a series circuit, right? There was only one path for current to flow. We've already said before, and we're going to keep saying it over and over and again, that current is common in series. And so the current was the same throughout. The voltages are different based on each one of those resistors. Here, notice now we're talking about Kirchhoff's current law. This is a parallel circuit. Everybody see how it's parallel? I've got multiple paths for current to flow. Go down and go to the right here, down to the right and through R3. And so I've got multiple branches for current to flow. This is a parallel circuit. And what Kirchhoff says about current is that current total is equal to the current in branch 1 plus current in branch 2 plus current in branch 3. And you can continue that on to however many branches it may be, right? So if you think about current total, the current total is going to be what leaves and returns to this source. Okay. Now, when it gets to this node, this option to go through R1 or continue on toward R2, some electrons are going to go down through R1, some are going to go through R2. This is really going to be based on the amount of resistance. So many times we talk about current, and we talk about electricity, and we talk about water. Just like water takes a path of least resistance, so does current, right? And so the greater the resistance here, the more current that would go in the opposite direction, and the less current that would go through R1. Here it says we've got, let's see, a branch current in 2 milliamps, 4 milliamps, and 6 milliamps, right? So it's saying through R1, we've got 2 milliamps. We had 4 milliamps that goes through R2. And we had 6 milliamps that goes through R3. Now, all of that current, the 2, the 4, and the 6, all of that current had to leave this source and return to this source. So if I took an ammeter, if I'm measuring current and I measure here, I'm going to get my 12 milliamps. If I measure in branch 1, I'm going to get 2 milliamps. If I measure in branch 2, I would get 4 milliamps. If I measure in branch 3, I'd get 6 milliamps. Now, how we got that exact, those currents, right now we're not given all the information so we could calculate that. It's really, we're looking at the point that what Kirchhoff says is that my total current is going to be equal to the sum of all these branch currents, right? So I had 12 milliamps, 2, 4, and 6 is going to give me 12 milliamps. So Kirchhoff's law holds true.
So the volts or the current is just basically like whatever the aggregate is across the whole circuit for both of Kirchhoff's laws.
Yes. Yes. And the thing is, when his law applies to the component that is not common. So for example, in a series circuit, current's common. So has the voltage law that expresses,
Okay.
you know what I'm saying? And in a parallel circuit, voltage is common. And keep in mind, let's say that this was a 10 volt supply. Well, I've got 10 volts across R1. I've got 10 volts across R2, 10 volts across R3. My voltage is common, and my current, the total current, is equal to the sum of all these branch currents.
Can you go back to that other slide?
Sure, absolutely.
It doesn't have a graph of that, but basically if it did have a graph of that, then it would have like it showing it why the resistors would be one arrow going up, one arrow going down, one arrow going up, indicating like the electron flow, I guess, right?
Yeah. And so gosh, I get a little happy there.
Right. So that graph that you just showed had all of them flowing down.
Mm-hmm. So the way it would look, and keep in mind, let me go back and I'll put this graph back up. For this particular circuit, right? So here's my supply. And since we're talking about a series circuit, and we're talking about this, right? There's R1, there's R2, there's R3, horrible as they look. And so current is common. Same current's flowing through this entire circuit.
Yeah, because it's flowing negative or positive to negative the whole way or whatever.
Yeah, exactly. It's
Or
flowing
negative to
negative.
positive.
It's flowing negative to positive, and so it's going down through all three of these. And what he says here, we know that current's common in a series circuit. However, these voltages, what he says about voltage is that the total voltage is equal to the sum of all these voltage drops. Right? This was 12 volts, and we said that across R1 was 2 volts, 4 volts, and 6 volts. That gives us our 12 volts. And so that's all he says there, is the fact that the voltage applied is equal to the sum of the voltage drops. When we go to the next slide, now we're dealing with a parallel circuit, right? Here I only had one way for current to flow. Everything that left the negative side of the battery had to go through and go all the way to the positive side. Now I've got an option for electrons to leave, go through R1 and come back to the positive side. I've got other electrons that are leaving the negative side, going through R2 and coming back. Then I've got another set of electrons that are going through R3 and then coming back, right? And so there's multiple paths for current to flow. And so therefore the current is what we're looking at in terms of his Kirchhoff's current law, because the voltage is the same. Parallel circuit voltage is the same across all three of those. It's the current.
The voltage is common.
Voltage is common. Yes, voltage is common in this parallel circuit. Yes. Current common in the series circuit, voltage common in the parallel circuit. Yes. Just to kind of reinforce some of what we've talked about in the past here. Actually, I'll put a little bit more information. So we said this was 12 volts. We said this was 2 volts. We said that this was 4 volts. and 6 volts. And keep in mind, these two circuits are completely independent of one another. And so I know that the 2, 4, 6, 12 combination seems to happen in both of these circuits, but there's no connection between these two circuits. What can you tell me, thinking about what we know in terms of Ohm's law, right? And we said that Ohm's law stated that voltage is equal to current times resistance. Voltage equal to current times resistance. We know in this series circuit, current is the same throughout, right? What could you tell me about the difference between R1, this top resistor, and R2, this second resistor? They've got the same current, right? So let's just say that let's do it this way. We know that for the top resistor, it's 2 volts is equal to say 1 amp times R, right? So that's what we basically have for this top resistor, 2 volts. We'll say it's 1 amp. Let me ask it this way. Is this top resistor larger or smaller than this second resistor?
The smaller.
Smaller, probably.
Okay, so the top resistor with a given current of, let's say 1 amp, that would mean that the resistance would be, the resistance is equal to voltage divided by current. If I did the math, I would say that this resistor is 2 ohms, right? If I did the math here, resistance equal to voltage divided by current, 4 amps, or 4 volts divided by 1 amp, I would get how many ohms?
4.
You get 4, right? So let's see if that makes any sense. Let's see. I don't want to clear all that. Let me give you a couple more values. Let's just do this. So total current is 1 amp. Got 2 volts. And then for resistance, if I solve this for resistance, resistance is equal to voltage divided by current, or in this case, 2 volts divided by 1 amp, or 2 ohms, right? Didn't mean to drag that down. I'll do the same thing for the second resistor. It's going to be 4 volts divided by 1 amp. It's in series, which equals 4 ohms, right? How about this last one?
It would be equal to
6
6.
ohms.
Be 6 ohms, right? Let's see if we can make some sense out of that. If I'm given Ohm's law, which states that voltage is equal to current times resistance, for a given current, any given current, the current's not changing. If I maintain that current, then the voltage will increase as my resistance increases. Let me say it this way. In order to get the same amount of current through a resistor, I would have to have a larger voltage developed across that resistor so the current was the same. Now, what you'll notice is when you have a series circuit with current throughout, the largest voltage is going to be developed across the larger resistors. The smallest voltage is going to be developed across the resistor that has the smallest value, right? And you can, just looking at the voltage drops, because we're in a series circuit, we're talking about this current flowing through it. We know that this resistor has to be twice as large as this resistor, right? Because of the proportions. This developed 2 volts, this developed 4 volts, same amount of current. This one's got to be twice as much. You can see this was 2 ohms, that was 4 ohms. We can make some inferences about this circuit as well. If we're looking at the current that's flowing through this circuit, we know that we've got 2 milliamps here. We had 4 milliamps here. We had 6 milliamps. Now, thinking about the relationship between current and resistance, all right, is current and resistance, are they directly proportional or inversely proportional? Current and resistance. If I increase current, do you think I would get more or less? As I increase resistance, do you think I'll get more or less current?
Less current.
Less current, right? If resistance goes up and the whole resistance was, the opposition to current, the more resistance I get, the less current I'll get. So with that being said, I had 2 milliamps, I had 4 milliamps, and I had 6 milliamps. Which resistor you think is larger? R1, R2, or R3?
R3.
All right, so we said that the higher the resistor, the less current, right? And so I had 2 milliamps through R1. I had 4 milliamps, so twice as much current through R2. And then I had 6 milliamps through R3. So even more current through R3. Which one has the least amount of current? 2, 4, or 6?
2.
2, right? So that means that R1 is the larger resistor of these 3. Because what happens, these electrons come along and they're going to say, oh, I've got R1 here. It's a larger resistor. So 2 milliamps worth of current will go this way, but the majority will continue to go this direction. And then they'll make that same evaluation between R2 and between R3. We're gonna see all of this once we start solving the circuits. And right now, like I said, you only have portion of the information. We're not giving you everything. I'm just thinking about some of the information that we already know and the relationship between voltage, current, and resistance. We can make some, we can notice some things and be aware. By the way, the other thing that Kirchhoff says about his current law, he says it this way in terms of the total equals the sum of the branch currents. He also says that if you go into a node, and this node is any place where I've got current going in and it's leaving multiple other directions, the current going into the node is equal to the current that leaves that node. So nothing is stored here. And so if you think about the values we've been given, we're saying that 12 milliamps go into this node. We have 2 milliamps that go through R1. So what's the amount of current right here? if we've got 12 going into this node, 2 leaving this direction, how much leaves in this direction?
It should be 12, right?
Well, keep in mind we had 12 here, right?
Right, but it's in parallel, so it should just always be 12 milliamps, right?
Now, remember what's common in parallel. Voltage is common, right? And so the voltage in this parallel circuit will always be whatever this voltage applied is. Across R1, if this is 9 volts, it's going to be 9 volts across R1, 9 volts across R2, 9 volts across R3. The current through these branch circuits will be different based on the value of these resistors. And one of the things that Kirchhoff states, the way he says it, is that the current going into this node. So let me see if I can put up here. Right, so 12 amps. Actually, he said 12, or for this situation, it's 12 milliamps. So I have 12 milliamps here. And then I know that I also have 2
flowing down. Oh,
2 milliamps flowing down, right? Let me move the, oops. So if I've got 12 going into this node and 2 that are leaving through R1, what's left?
10.
10, right? Okay, so I've got 10 milliamps here. And let's see if that makes any sense. So if I've got 10 milliamps going into this node, we said R2, the branch circuit for R2 was 4 milliamps, right?
Yep,
So
which
that
will
was
leave
4.
6 at the end.
Which will leave my 6 milliamps here,
And
which
then
is
6 milliamps in the resistor too.
which is exactly what went through R3, the 6 milliamps, right? And so that's another thing that Kirchhoff says is when you're looking at these points, that the amount of current going into a node will equal what leaves that node. 12 milliamp going in, I've got 2 going out through R1, 10 going this direction.
So you're
10
still at 12.
Yeah, you're still at 12. You're still at 12, right? You're still at 12. Now, when you get to this node, right, I'm only at 10 because I remember I've got 2 milliamps that are going to go right back this direction to the supply. They go back to the positive side of the supply. So here I've got 10 milliamps that are going into this node. 4 milliamps go through R2. That leaves me 6 milliamps, which is exactly what I expected through R3. Now, with that same philosophy, what do you think the current would be down here at the bottom of R1?
10.
Okay,
Is
10.
it's building back. Like I'm guessing it's building back. So we've got 6 coming up.
Yep.
And then 10 and then 12.
That's right. That's right. Yep. So, and that holds true to what Kirchhoff is saying. He said that I've got 10 milliamps here. Well, you had 4 that were coming through R2. You had your 6 that was coming. So you had 10 that's going in from 2 different directions and 10 that's leaving that node. Then you got into this node, your 10 from R2 and R3, plus your 2 from R1. And so right here, I've got my 12 milliamps again. Right.
So are the circuits pretty much always going to be built that way? Like you wouldn't have like a 6, say at R1 and then a 4 and then a 2, or does it matter? Like,
so are you asking me about the increasing amounts? Is it always 2, 4, 6? Is that what you're saying?
Yeah. Like, is it always like increasing the resistors that way, or does it just, depends on how the schematic's laid out?
Yeah. So no, it's not always increasing that way. And I turn it around and ask the group, what is the determining factor in terms of whether this is, the smallest current or the largest current? What determines how much current's going through each one of these branches?
The resistor.
Whatever you're needing to put load to.
Yeah. So we would design it based on whatever we needed for the load. But I heard somebody say it's the amount of resistance, right? And so resistance would determine how much current is going to go in each one of those branches. And I could have my larger resistance at R1. I could have my smallest resistor at R1. Really, that's not something that holds true, that it always increases or always decreases. It's just going to be dependent on whatever the resistor may be. Looking at this, going back to getting a feel for those relationships between current and resistance and voltage, looking at this, what I know is that my largest resistor is R1, because that's where the least amount of current goes, right? The greater the resistance, the lower the current. My voltage is remaining the same through all of these. And so what I could tell you, looking at the current, that tells me that resistor R1 is twice as large as R2. And resistor R1 is 3 times as large as R3 because of the amount of current that's going through R3. It's 3 times the amount of current. So therefore it's a third, if you will, in terms of the amount of resistance. I probably went above and beyond what you really needed to know there. And I may even have confused you a little bit, but what I really want you guys to do is just start thinking about those relationships. And I do know that some of the questions that you'll see, especially if timing is one of the most difficult pieces about the TKT, the more information that you have early as possible, the quicker you'll be able to answer the questions. In other words, we're going to see some questions later on where you can go through and do the calculation, and the calculation will take you, 2, 3, 4 minutes to do, or based on just some of the information that you can probably answer the question fairly quickly. We'll see some of that as we get into some of these calculations, especially about resistance. All right, any questions? Good deal. All right, so that was Kirchhoff's current law and Kirchhoff's voltage law. Talking about Joule's law, really when we're looking at power once again, and you see where it says simplify, this means that power is dissipated in the form of heat. And we talked about this notion that power is equal to heat. They also give you this formula for calculating power. P is equal to I squared times R. A lot of times that formula scares some people. Let me just give you an idea of okay, so the two formulas, if you can remember, voltage is equal to current times resistance. So that's Ohm's law, right? And if you can remember, power is equal to current times voltage. That's how we calculate power. Now, when they give you this, when they talk about Joule's law and they say that power is equal to I squared times R, I'll show you where they get I squared times R and what you can do if you want to avoid getting into either I squared times R or V squared divided by R. Basically what they've done is they have taken voltage out of the equation, right? And so they said, okay, power is equal to current times voltage, but I don't want to use voltage. I'm going to use what voltage is equal to. And so they write it like this. They'll say power is equal to current. And instead of voltage, what I'm going to do is I'm going to write what voltage is equal to based on Ohm's law. So Ohm's law says that voltage is equal to, so let's do it like this, times, I said that voltage is equal to current times resistance. You see that? So all I did is I took what voltage in this power formula, I took out the V and I put in what V is equal to, IR. Well, if I then calculate, or if I then multiply that together, I times I is I squared. And so I get, I squared R. the power is equal to I squared times R. This formula, power is equal to I squared times R. I show you that simply for the fact that sometimes people begin to get confused between, all right, what formula should I use? I want to calculate power. I'm not really sure. Do I use I squared R? Is it I squared R? Is it I squared divided by R? And all you have to remember is voltage is equal to current times resistance, and power is equal to current times voltage. Because if you can remember those two, it may take you one more step, but you can always find power, right? And so if I was given here I and R, well, if I'm given I and R, I can multiply those together and get my voltage, and then I can multiply that voltage by my current and get my power, which winds up being the same as this I squared R. Well, that's probably clear as mud, but you basically don't let this concern you. Don't let this panic you at all, because we're gonna do some power calculations, and you're gonna see you can use the same tricks that you use with power that you've used with Ohm's law, and it's going to be a real simple step to solve power. Okay. Here you go. Here's power, just like we did with Ohm's law, where we were looking at power is equal to current times resistance. Power is equal to current times resistance. I'm sorry, power is equal to current times voltage. Well, let me lead you astray. Power is equal to current times voltage. I can go ahead and cover up whatever I'm wanting to solve for. Here, if I'm looking to solve for current, current is equal to power divided by voltage. I want to solve for voltage. Voltage is equal to power divided by current. Or if I want to solve for power, power is equal to current times voltage, right? Once again, if you remember power is equal to current times voltage, you can then manipulate that formula to solve anything else. You can see this power is equal to I squared R. I showed you where they got that from. It was just a matter of taking out voltage and substituting in what voltage is equal to. So you wind up with IR times I, which is I squared R. They do the same thing here with voltage. Voltage squared divided by R. Well, now they've just taken current out. Current is equal to voltage divided by R, and they put what current is equal to. So you wind up with V times V over R, or V squared over R. All of that in the heat of the moment may get you confused. Stick with power is equal to current times voltage, and you can always, it may take you another step. Like I said, you may have to solve, instead of having just current, you may have to solve it for voltage, but using Ohm's law and using power is equal to current times voltage, you can solve any circuit that you want to. You can solve for any variable, voltage, current, resistance, power, all of those. And it's always fairly straightforward. Just trying to give you an acronym to remember the formulas. And the big thing is make sure that when you're talking about resistance, you're using Ohm's law. Voltage is equal to current times resistance. Power, it's current times voltage. Okay. We'll go back to this one slide just to make sure we're clear on this. Let's see. You see those review questions? Okay. Let me stop sharing that and try that. How about now? Okay. So just to recap, just to make sure, I know I talked about a few other things. Ohm's law. All right, if I'm going to solve Ohm's law for the three variables, the voltage, current, resistance, what is Ohm's law if I'm solving for voltage?
Current times resistance.
Current times resistance. Very good. All right. What about if I'm solving for current?
Current
Yes.
voltage divided by resistance.
Absolutely. And then what about if I'm solving for resistance?
Voltage divided by current.
Absolutely. Absolutely. So those, yeah, very good. Very good. So that's those three forms of the Ohm's law, right? And so if we feel comfortable with moving that formula around, we can solve for all three of those variables, any circuit that we're going to be given, right? We can, take a look at a resistor. If I know the value of the resistor and I know the current through that resistor, I can calculate the voltage. If I know, the voltage across the resistor and the current, then I can calculate the resistance. I can calculate whatever variable is remaining. Absolutely. What about Kirchhoff's voltage law? The voltage law. What does Kirchhoff's voltage law mean?
Power equals I squared divided by R.
Okay, so power is equal to I squared divided by R. I know they talking about when we get to talking about power, that is certainly one of the formulas that we're going to use to calculate power. But what about Kirchhoff's voltage law? And when we were looking at
current stays common.
Say that again.
The current stays common.
Okay, so in a series circuit, the current stays common. That's right. Now we're talking about, and Kirchhoff's voltage law is dealing with a series circuit.
Something to deal with the voltage drop. The voltage is the same as the drop.
Yes. So the voltage applied in that series circuit where we have that common current, the voltage applied is equal to the sum of the voltage drops. Absolutely. Right. And so all that means is whatever voltage is applied, it's going to be used. If we've got however many resistors in that series circuit, whatever voltage is applied, it's going to be used throughout that entire circuit. There's not going to be any remaining that we're going to store up somewhere.
If there's a remaining, there's something messed up.
Yes, that's right. If I apply 12 volts and I'm only getting 10 volts of voltage drops across, then what Kirchhoff really is talking about. He's saying that physically, and keep in mind a law. When you have a law, typically a law means that it's always going to be true, right? We're not talking about a law and
We're not-
out here,
Period.
a speed limit for rugs. We're not talking about that. We're talking about, a physical law, which means that, it's always going to be the case. And so what Kirchhoff is saying is that if you apply voltage to a circuit, that voltage is going to be used throughout that circuit. And if you do the calculation or you do the measurements, take the measurements, and you're missing voltage, well, that voltage is being dropped somewhere. That you may have additional resistance in the circuit somewhere. Something's going on. For us, this clean circuit that we have, this series circuit, all it says is that the voltage applied is equal to the voltage drops. Absolutely. So if that's the case for Kirchhoff's voltage law in a series circuit, what is Kirchhoff's current law? What does that mean? Once again, Kirchhoff is looking at the source, right? And here he's talking about current.
All the current will be used.
All the current will be used. Yeah, the current from the source is equal to the current in each branch of a parallel circuit. So all of it's going to be used. If I've got, remember our example, 12 milliamps. Well, in each one of those branch circuits, the total across those branch circuits was 12 milliamps, right? And so that's what he's talking about in terms of the current law, is that all of those electrons that are leaving the source, they're going throughout the circuit and they're returning to the source. They're not being stored up. They're not going to some point and just stopping. They are flowing throughout the entire circuit. That's also where, we looked at those nodes and said that, Kirchhoff made the comment about, whatever enters the node will leave a node. The current entering into a given node will be equal to the current leaving the node. And so, that's what he's talking about in terms of current. It's all going to be used. Power is dissipated in the form of what?
Heat.
Absolutely. Heat. Yeah, heat, most definitely. Right. And that's why it's so important that if we've got a circuit that has a lot of power, well, we want to make sure those components are rated for that power. And you'll see the resistors will be much larger, much more surface area. They can dissipate more heat. And then finally, the three formulas for calculating power. What's the one formula that we've got to remember?
That's the pi in
Yep.
here.
Yep. So got to remember pi, right? We got to remember power is equal to current times voltage. If we can remember that, then we can make adjustments for the other two. The other two, if I start substituting in what voltage is equal to, the voltage is equal to I times R. And so I get this formula, power is equal to I square R. Or if I substitute in what current is equal to voltage divided by resistance. And so I get power is equal to V squared divided by R. Both of those can be used, but if I know Ohm's law and I know power is equal to current times voltage, I can solve any for any of those components, any of those variables. Okay. Questions about that?
And you said we're gonna get in more depth as the lessons, as we go through the lessons.
Well, what's going to happen is we're actually going to put some numbers to it. And so when we start looking at series circuits and we assign values to the resistors and we're actually doing the calculations, it'll make things much more clear because, like when we were talking in terms of the series and parallel circuits for Kirchhoff's voltage and current law, it's hard to wrap your mind around it if you don't see exact numbers. And so I think it will become clear as you see the numbers once we start solving series circuits and parallel circuits. Should be next class.
Sounds good.
Okay. All right. So we are at 10 till. So we're going to go ahead and wrap things up. Like I said, I'll hang around. If you guys have any questions, feel free to hang around or ask questions now. Otherwise, go ahead and start working on some of those quizzes, go through the PowerPoints, and let me know when you have questions. Feel free to, I know we'll have class again on Monday, but if you got anything that comes up, shoot me an email, and I'll be able to work with you. So otherwise, if you don't have any questions, hope you guys have a wonderful weekend, and we'll see you on Monday.
All right. Thank you.
Absolutely. You too.